Class here is the physical laws warm-up exercise. I chose to do mine on the aircraft I currently fly, which is the Embraer 175, and it's by me, Morgan Shaw. First off, a little bit about the airplane, the aircraft information here. The Embraer 175, I'm going to do on the LR version. The max takeoff weight is 85517 pounds, or 38789.83 kilograms, and that's assuming the 1 pound to 0.454 kilogram ratio. The engine types, numbers, and rated thrust, as well as the total available thrust, sum of all engines. So it has the GE CF34-8E high bypass and dual rotor turbofan, fully integrated with nacelle and thrust reverser motors on it. And it's rated at 4,500 pounds of thrust per engine. Normal takeoff is derated, however, to 3,800 pounds of thrust, or 61410 newtons, assuming that conversion ratio right there to 4.5 or 4.5 newtons to 1 pound of thrust. The 13,800 pounds of thrust is the one I'm going to be using throughout this presentation. All right, so a little bit of the aircraft information continued here. So this chart on the side, this is what I used in order to calculate the takeoff distance at max takeoff weight, assuming dry, smooth, hard pavement, and level runway. And came up with 2,200 meters, or 7,216 feet. And then the conditions assume, like I said already, airports at sea level, ISA, and flat runway temp between -40 and 36 degrees Celsius. The speeds that I came up with for the aircraft was V1 was 152 knots, rotation speed VR 157, V2 is 158. Probably going to be using VR most of the time during this presentation for the calculations. And I converted a lot of this to meters per second. I prefer to deal with metric over the imperial system. It's much easier, and that's the conversion that I used right. All right, so the next problem I'm going to talk about here is acceleration, drag, and friction. First off, we're going to work through the acceleration equals force times mass equation, and this equation does not incorporate friction or drag in it. I'll get to that in just a little bit. But so starting off with this force, we have engines that produce 3,800 pounds of thrust per engine, and 3,800 pounds of thrust times 2 engines, that's 7,600 pounds of thrust. So we'll use that number for this. And then mass equals weight times acceleration of gravity. The weight for this aircraft is 85517 pounds for the max takeoff weight, and the acceleration of gravity is 32 feet per second per second. That comes out to be about 2672.4 pounds per second squared per foot, and that's unit is also called a slug. And then we plug that into our equation. So A equals 7,600 pounds of thrust divided by 2672.4 slugs, and we get 2.84 feet per second for acceleration, without assuming those two other factors I already talked about. So now we'll get into that part of it. Acceleration equals T equals thrust, D equals drag, and F equals friction. So we'll go ahead and calculate those and see what our acceleration comes up with. So first off, to do this, we got to figure out friction, and friction involves getting our lift coefficient, and our lift and the lift equation is right here. It's coefficient of lift. R equals is for density. V is velocity squared. A is the area of the wing divided by 2. And so the first off, coefficient of lift, calculating that's going to be 2 pi times A, which is the angle of attack expressed in radian. I'm just assuming a 5-degree angle of attack here, just kind of throwing that out there. And that ends up getting us a coefficient of lift about 0.5, so that's what we'll use in the equation. The next thing, so R, that's the density of the air, and I'm just assuming standard, which is at about 0.0765 pounds per foot cubed. And then the area of the wing on the Embraer 175 is 783 feet squared. Okay, so from there, we'll go ahead and calculate the lift. We plug it all into the equation, divide by 2, and assuming 10 knots, that's just the number that I picked to try to figure out what our lift would be if the aircraft's moving at 10 knots. and we ended up getting about 4,277 pounds of lift. Then the next thing here, we want to plug it into our friction equation. So our friction equation, U is the friction coefficient, which for general tarmacs, usually it's around 0.02, so that's the one I used. And so we're going to take that 0.02 times it by our W, which is the weight, so 85517 kilogram, or sorry, that's supposed to be pounds. I'll change that. And then minus 4,227 pounds, and it ends up coming up with about 1625 pounds of friction force. All right, so the next part of this, talking more about acceleration, drag, and friction. We figured out the friction number here, and now we want to figure out what drag is, so we can put it onto our acceleration equation. So drag is equal to the drag coefficient 1/2 r, which is air density again, velocity squared times the area of the wing, and so first thing we want to get is our drag coefficient, which the number's not really published a whole lot, but I found on an engineering website there was this drag coefficient for a pretty normal jet aircraft wing. It was a 0.05. Embraer doesn't publish that number, so I just went with this. I think it should get us pretty close. R is, again, it's the air density, and V, velocity. We're assuming 10 knots, which comes out to 16.9 feet per second, and then the area of the wing again is 783 feet squared. So drag, we plug that all into the equation, and we come up with about 428 pounds of drag when we're going 16.9 feet per second velocity. And so we have our drag numbers now, so now we can plug it into this acceleration equation. So A equals our thrust, so 7,600 pounds, minus D, which is our drag, which we just calculated, 428 pounds, minus friction, which we calculated earlier, as well as 1,625 pounds, all over mass. So remember, mass is weight divided by the acceleration of gravity. So our weight is 85517 pounds divided by 32 feet per second, and we ended up with 2672.4 slugs. And if you calculate all that out, we end up coming up with about 2.07 feet per second. So again, it's a little less than our area equals force divided by mass, but it is pretty darn close. So that's how you kind of factor all that in there. And if the drag and the friction obviously are going to change as the aircraft accelerates and as the weight gets off the wheels, and as you get different sorts of drag, induced drag, parasitic drag, all those things from increasing speed. But this is kind of just giving us a good snapshot time, kind of where sort of what the aircraft's doing at a certain point. All right, so now we're going to go ahead and calculate the time it takes the aircraft to take off. So from start to rotation speed. Now rotation speed, like we talked about in the beginning, VR is 157 knots, and if you convert that to feet per second for our calculation, it ends up being about 165 feet per second. And then we're also going to take the acceleration rate that we calculated in the last slide, that 2.07 feet per second squared. And to calculate this, we're just going to divide 165 feet by the 207 feet per second squared, and then ends up coming out to about 79.7 seconds. So it takes us 79.7 seconds if the acceleration rate remains constant in order for us to reach the rotation speed. This acceleration rate is not going to remain constant just because of the drag's going to change, friction's going to change. It's all going to change as we're getting faster and faster. All right, next part of this was the energy calculations. So the first part was calculating horsepower, which the book gives us this nice horsepower equation. Horsepower equals thrust times your speed in knots divided by 325. And so you plug numbers in there and just kept it in imperial this time. So 27,600 pounds of thrust between the two motors, 157 knots. Rotation divided by 325 is equal to 13332.92 horsepower. And then the next part was calculating potential energy, which is weight times height. This is in foot-pounds. And so assuming the aircraft has burned off about 500 pounds of gas, which has reduced its weight from 85,517 pounds to 85017 pounds. And then in return has gained about 1,000 feet of altitude. So if you plug those numbers in there, your potential energy comes out to be about 85017,000 foot-pounds. The next part was the kinetic energy aspect of it. So this formula here, again from the book, 1/2 mass times velocity squared, and that's again in foot-pounds. And so if we assume the aircraft is at VR, so 157 knots once again, and has maintained its max takeoff weight of 85517 pounds, then you plug the numbers in there, and the kinetic energy comes out to be about 10539542666.5 foot-pounds. And then for total energy, it's simple. You're just adding those two, potential energy and kinetic energy together, and you get that number there, 11389712666.5 foot-pounds. All right, now the final problem here was clearing the obstacle. So the scenario that I kind of came up with was, so we need to clear an obstacle that's at 500 meters from our point of liftoff, so the 500 meters from the point of rotation, and it's at a height of 50 meters. So if you draw this out, you've got a nice triangle, and like I said, so we're gonna look for we know the opposite side of our triangle, so we know the obstacle's height is 50 feet, and we also know our adjacent side to the angle we're looking for, which is 50 feet or 500 meters. And so if we want to solve for that, we know that we have a tangent function, which will give us that angle. So tangent, if you remember, is opposite over adjacent. So tan of x, like I said already, is 50 meters divided by 500 meters. So that gives us 0.1. So now we want to solve for x because we want to get that angle. We want to make sure that if we plug this in our calculator, it's in degrees and not radian mode. So we take the inverse tangent of 0.1, and it ends up giving us about 5.71 degrees of angle. So what that tells us is if this was actually the real scenario, we'd need to have the aircraft would have to be flying at an angle of 5.71 in order to clear that obstacle at the bare minimum.